Okay, I think it's going. All right, the exam review. Okay. Again, Adler is super crazy and changes everything drastically every year. My exams were free response. There used to be no online homework. He just started this weird, what's the name where you have to like edit stuff?
Perusal.
Perusal, yeah. So it's really hard to know what he asks, but it's typically 1/3 mastering physics, 1/3 book problems, and then 1/3 old problems or like theoretical problems. But he's gotten even less into mathematical questions. So I'm more going to prepare you for what he typically tests for. If anything, what you want to abstract from this is the main idea and how to approach the problems. The difficulty could be then interpreting what he's even asking for. But this is at least typically what he gets into. So he doesn't actually, I've never seen a single chapter 1 question, but you guys did chapter 1, so we're going to go over it anyways. So we have cross product versus dot product. A cross B equals AB sine theta, and A dot B is equal to AB cosine theta. Okay, there's more formulas and there's more you could do, but we're going over what I think is the big picture here. And also just to make sure we get through everything. So let's say this is B, and it's 10, and A is, I don't know, 15. And the angle here is 120 degrees. So the easy way of telling you how to do this is just go ahead and plug it in the formula. In this case, it's going to be 15 times 10 times the sine of 120. Sine of 120 is 0.866. 866. So 129.9. 129.9 newtons. That's the mathematical way. Another way of thinking about this, the cross product, you want the component of B that is in the same direction as A. So if I rewrote this again, I could say, okay, A is going this way, and did I say same direction or perpendicular direction? It's perpendicular direction for cross and same for dot. So essentially I would take this and I want to say that this is A and this is B. They're clearly not exactly perpendicular, but if I split this up, I can get a B perpendicular value and a B parallel value. It's basically going, well, this is actually anti-parallel, but nevertheless, we're more interested in the perpendicular, which is this one here. So B perpendicular, if we were to solve for this, so this is 120, that's 30, which means this is 60, yeah, 60 degrees. And solving for B perpendicular, I'm going to take, this is 10 going in this direction, and 10 cosine 60 is
why is it 60?
It's not, it is 30, yeah. All right, so this is 30 degrees. It's a little harder to find out the perpendicular when they're at weird angles. It would work better if they were going the same angle. But yeah, this is 30 degrees, and that would explain that. So if you were to just...
The perpendicular needs to be 90.
Yes, so yeah, you're right. So, and then I was kind of realizing it as I did the math. So this is 30 degrees. So if we're looking for B perpendicular, this is going to be equal to 10 cosine 30, which gives us 8.66. So essentially, if I rewrite that, we have A, which is going in this direction, and the perpendicular component of B to A, this sign means perpendicular, is equal to 8.66. And 8.66 times 15 gives you 129.9, 129.9 newtons. So let's say we're doing the dot product now for the exact same thing. So for the dot product, we're just going to plug in 15 times 10 times cosine of that angle between them. It's important that they're tail to tail. So this wouldn't work if it was like head to tail or anything. But basically 15 times 10 times cosine of 120 gives me negative 75, which is okay to have. AD equals negative 75. So I did the exact same thing, but instead of saying sine 120, I just said cosine 120. And the idea for dot product, so if cross is where you want the perpendicular component, dot is where you want the parallel component. So instead of solving for this, I would have solved for B parallel, and I would have gotten that it was equal to negative 5. Negative 5 because it's going in the opposite direction. It's going this way. A is going this way. I have to make one of them negative. I could have just made A negative, but let's make A positive and B negative. In which case it's 15 times negative 5 still gives you negative 75. At the end of the day, as long as you know the angle and you plug them in, you'll be fine. Like the quicker, more Adler-esque rule of thumb is that for things that are perpendicular or have any level of perpendicularity, this is A and this is B, you will have a cross product because we want the perpendicular component of B and A. So if I have something like this, great, this has a cross product. But why doesn't this have a cross product if I have A and B going in the same direction? What's the angle between two things when they're in the same direction?
0.
0. And the sign of 0 is 0, so you won't get a cross product in this case. Similarly, if I made them A and B, well, this is now 180 degrees. Same thing, if I did sine of 180, I would also get 0. So you're not going to have a cross product here or here. As far as dot product, you won't have any dot product when they're going completely perpendicular, because here the angle is 90 and the cosine of 90 is 0. Another way to think about it is the dot product is where you want a component of B that's in the same direction as A. There's no way I could break up B to have it going at all in the same direction as A. So that is probably more likely to be the question. He'll give you a bunch of vectors, A, B, C, D, E, F, and he'll say, which one of these have possible cross products, which one have dot products? The last thing about this, then we'll move on because it's stupid and irrelevant, is what's the direction of the vector when you did the cross product? Let's say in this case. So what you want to do is you want to take A and B hat. Actually, shoot, I wish I had my book. Did I give you B hat A or A B hat? Does anyone have notes on this? Whatever one I gave you before was good. I just haven't done this in a few weeks. So I want to be that. I don't want to give you guys the reverse of what's the right thing.
You first put your hands in the direction of it.
So I used a different one because I hate everything about the book. AB hat. And this is A cross B. Does anyone have the book? Nah, that's true. I'm gonna go with A, B hat. And if it's wrong, I'll send everybody a thing just saying flip your hands, it's actually B hat and A. But if it is this, then you'll say, okay, A is going in this direction, No, I take it back. It's definitely yeah, I'm gonna go with AB hat, and I'll just send you guys a correction if it's not this. In which case it's gonna go up, because this is, it's gonna go to the right, and then the B hat is going up, and it's gonna come out of the page at us. So that would be in the positive Z direction, out of the page is where the resultant vector would come. Also always remember that A cross B is going to be the opposite of B cross A. So in other words, if I said this was A, and this was B, makes this A hat, the answer would be into the page. It would be the exact same magnitude, everything, just opposite direction. Yeah, so actually, you know what? I'll confirm either way, just so no one's like stressed about it, whether or not the hand should be drawn one way or the other way. Okay, cool. All that's useless, but he might ask it because he's really unpredictable. Let's see, what did I have? Displacement versus time graph. Okay. Delta x over t. And let's say at t is 0, so let's say they just give you a bunch of points. They say, they give you a chart, which sometimes they do. So here we have t, here we have delta x. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, I need to work on the tables. Okay, so this is negative 40. This is, this is negative 10. Negative 10, then we have 0, then we have 10. Then for t equals 3, we also have 10. For 4, we have 20. For 5, we have 40. For 6, we have 80. 80. So 20, 40, 80. And then for 7, we have 70. And for 8, we have 60. So I'm just going to plot all of these points and then just somewhat connect the dots. So dot 1, so we have 1, 2, 3, 4, 5, 6, 7, 8, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, negative 10, negative 20, negative 30, negative 40. So I'm going to start here. Actually, no, sorry, it starts at negative 10. So we're starting right here. The next one is t equals 1 and 0. And then we have t equals 2 and 10. And then t equals 3 and 10. So t equals 3, delta x equals 10. T equals 4 is 20. And t equals 5 is 40. So 30, 40. And t equals, so this is 1, 2, 3, 4, 5, 6. So 6 is 80. So 40, 50, 60, 70, 80. And then I have 10, 20, 30, 40, 50, 60, 70, 80. Should go up a little higher actually. And then 7 is 70 and 8 is 60. So if I connect all of these dots, it looks kind of like this. And that's exactly what you should do. If they give you a table like this, you can just connect the dots straight up. And we'll go through all the qualitative questions, and then the harder version of that is draw the velocity versus time graph, or draw the acceleration versus time graph. Cool. All right, what is the change in displacement from t equals 2 to t equals 0? From t equals 2 to t equals 0, we do have a positive change in displacement. Oh no, that's okay. So this is going from 10 to negative 10. So we went up 20 meters, sort of towards our goal. We were always imagining the finish line is kind of what we're trying to get to in a y direction. We want to get there, and this is the bad. We don't want to go here. Bad. So anything that goes towards the finish line is a positive change in displacement, is a positive velocity. What about the velocity from 0 to 2? Is it positive or negative? Positive. And for that, it's a displacement versus time graph. When you have displacement, to get the velocity, you just try to find the slope. And let's say I wanted to get to the acceleration. What would you use to get to the acceleration? Slope of the velocity. What if we didn't have the slope of the velocity? A quicker way, I mean, that's absolutely right. If you have the velocity, you just want to find the slope again. But if we didn't have that, if we only had a displacement versus time graph, we're basically going to look for the concave up or down. Anytime it curves up like this, it's a positive acceleration. Anytime it slopes down like this, it's a negative acceleration. So there is no slope from 0 to 2 seconds, so there's no acceleration. There's just a constant slope. And we can actually find what the velocity is. Finding the slope is just the change in y over the change in x. So from t equals 2 to t equals 0, we can say that the final y is 10 minus the initial y, which is negative 10, over the final time, which is 2 minus the initial time, 0. And this should give us 20 over 2 equals 10. That's exactly how you would find the velocity. From t equals 2 to t equals 3, there is 0. Yeah, we're not moving. So what's going on from t equals 3 to t equals 6? It's curving. Does it look concave up or concave down? This is concave up, which just means it's a positive acceleration. And in this case, we really don't have the tools to find out exactly what it is, so it's enough just to say that it's a positive acceleration. Then what about from t equals 6 to t equals 8? It's a negative velocity. We can specifically find out by saying 60 minus 80 over 8 minus 6, we would get negative 10 meters per second is our velocity. Cool. Let's say that they asked for the velocity versus time graph. Remember, you guys don't have to draw these. You just have to be able to like read them, essentially. But if you did have to draw them, which would be even harder, we're going to say that the velocity starts out immediately from 0 to 2. It's at 10, but it's a constant of 10. So curves on a graph, like the derivative of a curve, will be a straight slope. The derivative of a straight slope will be a straight line, a constant. The derivative of a constant will just be 0. So this is just a straight line. So the derivative of this graph will be this graph. So it's just a straight 10. This is from 0 to time 2 seconds. What happens from 2 to 3? We said that the velocity is 0. So we're literally just going to go from 2 to 3. The velocity is 0. And then from 3 to 6, it looks like it accelerates. And we can actually measure this. We're not going to worry about it too much because there's a lot of stuff I want to get to, but we could measure it by saying that it's going up. It goes 10 meters per second, and then 20 meters per second, and then 40 meters per second. So it's increasing at a rate of 10 meters per second. Actually, no, I guess it's not. The acceleration might be a little bit more erratic, but it is accelerating, regardless of what it is. So from 2 to 3, nothing, and then from 3 to 6, there is a big, just kind of like jumps up immediately, and then it, from 6, and then it immediately goes down. So we're gonna cut down here, and we go down like this. So it's gonna look weird. Nothing would actually move like this. Nothing accelerates dramatically and then stops and immediately reverses. But more or less, this is the graph that you would pick when you have to go through A, B, C, D. You don't have to draw the graph, and they won't give you two graphs that are like, pretty similar. The idea is that it's like the constant velocity, it stops. And then suddenly it starts accelerating, and then it immediately starts decreasing. Actually, you know what? I take that back. This last part is wrong. It doesn't start decreasing like this. It goes immediately to negative 10. This is a velocity of negative 10 meters per second squared from 6 to 8. But even that, I don't think that they would give you, like the graph's gonna be pretty straightforward that you're picking the right one, where it's got a positive velocity versus a zero velocity versus an acceleration versus a negative velocity. And the acceleration versus time graph would be even more boring. The acceleration versus time graph, what's our acceleration here, 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 here? It's at 0 up until you get to 3. And at 3 seconds, so it's here, and then we have time of 3. So from 3 to 6, it's accelerating at some value to 6, and then it's immediately going like that. So there's only acceleration from 3 to 6 in that case. From 0 to 2, we had constant. From 2 to 3, we had no movement. And then from 6 to 8, we had a constant negative velocity. Again, drawing them harder than picking them. So as long as you can read them and be able to say, oh, that's 0 acceleration, then a positive acceleration, and then 0 acceleration. This is a positive constant velocity, then 0 velocity. And then an increasing velocity, which must mean acceleration, and then a negative velocity. That's the takeaway at the end of the day. Also keep in mind that you can find the displacement using the velocity versus time graph. So if I wanted to go back from velocity to the displacement, I could take the integral, which is basically the area. So in this zone right here, if they ask for what's the displacement from 0 seconds to 2 seconds, I could just find the area here and say, okay, well that's 2 times 10, that's 20. That's 20 meters. We went 20 meters in 2 seconds. I can do all of that with the velocity versus time graph. In this case, I didn't have to because we already kind of figured out that it was 20 meters.
Why does the velocity jump at 3 rather than just like going up from
That we have to go with, because they only give a snapshot, 0, 1, 2, 3, 4, 5. You're right, nothing ever really jumps, so it probably more realistically jumped from there. But given the data we have, it goes from, so from 2 to 3, our velocity is 0.
Right.
And then the very next second, it's a positive velocity of 10.
Okay.
But during that time period, it's accelerating. So we don't really know for sure. You're absolutely right. It could have started from here, but because there's no, like, it's not 3.1, 3.2, 3.3, we don't really know. But they're not going to give you 2 separate graphs like this, and you have to pick the right one. It's going to be a lot more clear cut. 2 of the graphs are going to be garbage. One of them is going to be okay, and then one of them is going to be the right one. But they're not going to split hairs that much with you. Cool. So that's graphs. I've seen a lot more graphs. So usually he doesn't ask many graph questions. There's usually like 2. But I've seen so many more graphs with y'all than I normally see. And he's erratic, but I would say he usually does test on the stuff that he gives you. So as erratic as he is, I don't think he'll give you a bunch of work and then test you on completely different stuff. He has done that for some exams though. So really, I've been wrong so many times before about what he'll ask. So I'm just giving you all of the concepts you'll need and not worrying so much about the particulars. Okay, so swimming. I want to see, is it still working? Yes, okay. If we're in a river, we're swimming in a river, the river is 100 meters across, and we're swimming at 20 meters per second. But it's a really, really strong current. The current is a straight downwards, downstream, 10 meters per second. I want to know exactly what is my change in displacement. They could also say distance in this particular case, but what is my change in overall displacement from my starting point here? Let's say they do say distance, just to avoid ambiguity, but they could say displacement. There's a couple different ways they could ask the question. Well, first of all, 20 to the right and 10 to the down, that's x and y, and those are relatively separate. So how long is it going to take me to get across? It's just going to be, delta x is 100 meters. My velocity constant is equal to 20 meters. All right, and my time then, if it's, my acceleration is 0. They don't tell you acceleration. They don't always have to say constant. If they just say your velocity is 20, and they don't say anything else, assume it's constant. In this case, I could say delta x is equal to velocity initial times time plus 1/2 acceleration times time squared. So this is 100 is equal to 20 times t, and that's maybe intuitively you figured it out, but that's at least how we would write it mathematically. It takes 5 seconds to get across. And I've said it a couple different times before to those of you who I see regularly. The time is the same for the x and the y. So it's also 5 seconds in the y direction then. If it takes me 5 seconds to get here, I'm falling for however long 5 seconds is. And I know that the velocity going downwards is 10 meters per second. And the acceleration is 0, and this is just constant vc. So I can do pretty much the same thing. Delta x equals vit plus 1/2 at squared. And that's we'll call delta y, is equal to the initial velocity 10 times the time, which is 5, and that's 50 meters. So I went 100 meters this way, but I also went down 50 meters. So I kind of land somewhere around here. I basically swim like this because of the current. Now if they ask for the distance, that means they don't really care about the x component, the y component. They just literally want to know, how far away are you? Just straight up, don't even give us like a direction. Well, for that then I'd have to take the fact that this is 50 meters down, and that's 100 meters to the right, and I have to do Pythagorean theorem to figure out what is the actual straight up distance hypotenuse from there. 100 squared plus 50 squared, square root of that is 111.8. Cool. And yeah, so that would be the answer to this, 111.8 meters. And they could ask what's your speed that you were swimming, and that's pretty much the same thing. There you're just combining the 20 and the 10 as x and y components, and also solving for the hypotenuse. So if they ask for scalar, they're very often just asking for give us the hypotenuse. Similarly, if they give you the speed, they're giving you the hypotenuse a lot of the time. Okay, so Evel Knievel is about to go off a ramp, and his velocity, they'll say his speed as he goes up this ramp is 50 meters per second. He's going to go something like this. They want to know two things. What's his range? Range is delta x. And I've done problems like this with a lot of you, but this is just covers every type of thing that you need to know that I think it's good to do again. What's his delta x? What's his range? How far did he go to the right? And how much bigger is the speed that he hits the ground with compared to his initial speed and compared to the speed at the maximum height? So A, delta x, B, speed bottom versus speed initial versus speed max h. It's kind of a vague question, but it's okay. So immediately, we get angry. We hate angles. We don't want angles, so we need to break this into a right component and an upwards component. This will be 50 sine 30, which is 25. Call that Vy. And then this is 50 cosine 30, which is 43.3. Great, that's the first thing. Like, first thing, technically that's the second thing. First thing, picture. Second thing, break apart the x and the y. Third thing, draw a good table. I'm talking about the table specifically when it goes from here to here. I'm calling that the full journey. So this is a full journey table. The Vx in this case is 43.3, but that's also the Vy because the acceleration is 0, and it's usually less helpful when we have a constant velocity. We can't solve for as much. In fact, whenever it's a constant velocity, of our three equations, delta x equals vit plus 1 half at squared, v final squared equals v initial squared plus 2 acceleration delta x, and v final equals v initial plus acceleration times time. If it is a constant velocity, you can only ever apply that to the first of the equations. So we'll keep that in the back of our head. So it's usually it's more difficult to solve for variables when you have a constant velocity. And that means probably we need the y to come in and rescue us. But we'll get to that. Like, that's just a rule of thumb. Won't always apply. We're just gonna approach this like we would approach anything. I don't know the time, and I don't know the delta x. That's actually the first thing they want. Now the y I do know. The y is 25. So which directions have I already implied are positive? Which two? Which ones? So I said 43.3, so that's to the right. So I'm just saying that's positive. That should be, intuitive to say that's positive. So we're saying it's positive. I'm also saying up. I'm saying up is positive, which is not intuitive. Sometimes down is positive. Not here. Up is positive. So my Vy final, this is initial. V final is, we don't know. Our acceleration, well, it's planet Earth, so it's gravity. 9.8 down. Down means negative. Delta y, and t we don't know either. Delta y. So this is a 100-meter tall cliff. The delta y is not 100 meters. That is the number one mistake people make, and I'm making a big point about it. Because we have just made a big deal about it's 100 meters below where we start. That means that it's negative 100. So do not be the person who screws it up. And if you have three variables, you can solve for a fourth variable. Because of our equations, delta x equals vit plus 1 half at squared, and v final squared equals v initial squared plus 2a delta x, and v final equals v initial plus acceleration time. You guys should know these, and they'll give them to you, but his formulas suck. So look over the formulas that he gives you before you go to the exam, because he gives you like 50 formulas, and they're all really confusing looking. So you need way less formulas than he gives you, and even the ones that you do need that he gives you, he somehow makes them more complicated than they should be. But if you ever have three variables, you can solve for the fourth variable. If you only ever have two variables, that's where life gets more complicated, and you have to be smart. That's going to be the next question we'll do. Question?
Well, he said that he's like giving us copies of the textbook that have paragraphs explaining what they are.
For the formula page.
Yeah.
If he is, that's completely new, which would be great.
He's giving us the summary pages. He said,
Oh.
Did you see the email he said?
That's good, because he has the most convoluted formula pages I've ever seen.
Well,
So
I
that.
Is that the exam?
I thought he was just giving us the form. That's what is it?
So I have no idea what he's gonna do.
That would be awesome.
It'd be awesome if he does.
I did
Be
not-
prepared for the worst case scenario, which is that he gives you dog shit formulas.
Did he post a
He
sample
said,
of a
okay,
little
formula
like-
sheet confirmation. Dear students, after being asked a few times today during office hours, I thought it would be good to clarify the following item about the formula sheet you will get with exam 1. Attached to exam 1 will be a copy of the formula sheet I posted to Emily classes, including the text and graphics.
Well, you're right.
Like, I didn't believe it, but
Yeah.
that's what it says.
You're right.
So,
That was like there's a lot of information.
yeah, so
It
the
was like
equations
chapters
from the
somewhere.
textbook are fine.
That's
Okay.
a lot, though.
So that would be great if he gives you better formulas. In any case, even the book sometimes makes the formulas more confusing. You guys should know the formulas. not just because I want you guys to know them, but you won't get the grade you want if you haven't done enough problems that the formulas are burned into your head. And there's 3 from chapters 2 and 3 combined that I believe are necessary. And then there's only 1 from chapter 4. I mean, that's like 4 formulas basically. I guess the chapter 1 formulas, those are hard. So if you guys have a cross product where he gives you the XYZ values, that's a pain in the ass. That you absolutely just plug it in the formula. But if it's chapter 2, 3, or 4, you really have a very few number of essential formulas. It's a lot of analytical stuff. I mean, you could technically think of Fg equals mg as a formula, but I don't even think that's like a formula. That's just what the force of, technically it's a formula, but it should not be so many formulas, and you should know them. But I agree, that's great that he's giving you guys the thing, because I've had people who haven't even wanted to meet with me for tutoring. They're like, I just want you to, I'll pay you for 10 minutes of your time, explain the formula sheet to me. And that's the only time I've ever seen them. So yeah, there is notoriously bad formula pages. So it doesn't surprise me that he's giving feedback and it's changing them. That's great. Okay, back to this. So we have 1, 2, 3 variables. Whenever you have 3, you can plug it in and solve for something. Okay, I want let's see, I have the delta y, so I can do that. I have the initial, so I can do that. I have the acceleration. I can solve for the time right off the bat with this, just the first formula. I didn't even think about it. I just went with the first formula and it worked. So delta y in this case is negative 100, which is equal to the initial velocity, negative because it's down, 25 because it's up, times the time, plus 1/2 times the acceleration, negative 9.8 because it's down, we set up as positive, times the time squared. I'm going to just basically add 100 to both sides, which makes this 0 equals. 0 equals is the same thing as y equals. So basically you want to get it so that it's 0 equals some bunch of numbers. Because this is a quadratic, and I hate doing quadratics, so I'm going to graph it. 25x plus 1/2 times negative 9.8 x squared.
I don't mean to be super nerdy, but if you YouTube how to program the quadratic formula onto your calculator, it's really easy. I did it in like 5 minutes.
Yeah, I know. So some people have calculators that can automatically quadratic solve it. I didn't know there was a way to download it, but that's great.
You can just like follow it and program it into your calculator. So I recommend it.
Yeah, that's fine. Whatever way gets you the answer the quickest. I'm fine with you guys like putting stuff in your calculator. You're probably not supposed to, but
well, it's not like you would still have to understand.
No, I mean I think you should be able to, but I'm saying they might. I wouldn't like say, hey Alec, can I have this on my calculator? Because they'll probably say no. Or and if he did say anything, then he'd be like, oh, I don't know. But yeah, I mean later you don't have so many right now, but especially later, it's really important to save numbers on your calculator, just to save time, and because the numbers are like, huge or really small numbers, it makes calculations a lot quicker and more reliable, so you don't put in the wrong number. Anyways, whether you do the super quadratic by downloading that thing, or you graph it, or you be more of a nerd and write it out, you'll get the time is 5.1. So it takes 5.1 seconds to go here. I know that because we said this was the full journey. So that time is specifically the time from here to here, which is 5.1 seconds. And they want to know the delta x. So we know 5.1, but we know the one thing x and y have in common is the time. So this is also 5.1. And now I have all variables except for this. So I can take this top formula. Remember, this top formula is the only one that works for constant acceleration problems. We couldn't have done it earlier because we didn't have enough variables, but now I can. Delta x is equal to the initial velocity, 43.3, times 5.1, plus 1/2 at squared. Well, the acceleration is 0, so we don't really care. So 43.3 times that time is 220.9. 220.9 meters. Okay, cool. They want the speed that it hits the ground. the speed that it hits the ground, speed implies hypotenuse. So okay, this is the answer to A. Now, and this honestly would just be one question, but let's say it had been a different question. Part B. The speed that it hits the ground. The speed which it hits the ground is a combination of the Vy with the Vx. And speed means hypotenuse. The Vx has never changed. It's a constant acceleration of 0. So its initial horizontal velocity was 43.3 to the right, and its final horizontal velocity will also be 43.3 to the right. Things don't tend to accelerate in the x direction when they're thrown. The y did accelerate, it accelerated downward. So the y went up with 25, it was 0 at the top, it started going down faster and faster and faster and faster and faster, and it should have like, we would predict that the velocity at the very beginning, well, we know it's 25, and then it should be 0, and then it should be negative 25 as it passes the initial height with which it fell, and then it should be like negative 30, and then it should be like negative 35 or 40 or something, right? It should be something bigger than negative 25 going down. And we can, forget conjecture, right? That's just predictions. We can easily find out what the final velocity is. I have 1, 2, 3, 4. Somebody pick a formula, 2 or 3. Which one do we want to use? 2. Okay, 2. It doesn't even matter. So I want to know what the final velocity is in the y direction. So that's v final squared is equal to the initial 25 squared plus 2 times the acceleration, which is negative 9.8, times the displacement, which is also negative, times negative 100. And I'm just solving I could have used the third one too, it didn't matter. That's the whole idea, is that it just really doesn't matter. You can just solve for stuff, and it turns out to be right using this kind of approach. 25 squared minus 19.6 times negative 100. And I'm getting 50.84. Vy equals 50.84. 50.84 down. It's technically a negative number. But by saying it's down, we don't really need to worry about the negative. And well, combining this, x squared plus y squared equals z squared, it's the Pythagorean theorem, plus 43.3 squared, square root of that, 66.8. That's the speed. 66.8 is the final speed. So I just kind of making up how we're going to compare it, but that's the final speed. What's the initial speed?
You can plug it in.
Well, technically that's what they use 50, right? They said you're traveling at 50. They could have said it was 43.3 and 25 up, but the speed is just that hypotenuse thing. So it would have just been 50 is your starting, your final 66.6. So this is 16.6 greater. They also could have said, what's your speed at the top? And this is more important and more difficult. No.
Say 0.
It's 0 in the y direction. So that's important. Our y velocity is 0 at the top. Right? X and y completely separate. So at the top, we have no velocity. Well, the speed is always x squared plus y squared. So that is very important that at the top we have no velocity. So it's 0 squared. Sam, what's the speed at the very top? Or what's the Vx at the top? 43.3. It's Vx is 43.3, 43.3, 43.3, 43.3. So if it's 43 in the x and 0 in the y, that just means that the speed at the top is equal to 43.3. And sometimes they screw with you guys by saying the speed at the top is 43.3, and then somehow you're supposed to start the problem by realizing that the Vx is 43.3. They'll just change this problem up by changing the variables, and you'll just plug them in. That's by working blindly, you don't have to worry about what direction you're going. You just have a picture, you have a chart, you have the formulas, and you're just like a monkey just like plugging the stuff in, and then you'll get the right answer. You just have to, of course, realize certain things like speed at the top is Vx, the Vy at the top is 0. You have to break up things into x and y, etc. Okay, cool. Let's go on to the harder, more realistic exam problem. So it's easy when you only have three variables when you do have three variables and you just plug them in to get the fourth variable. It's difficult when you only have two variables and you have to be savvy and realize that you have different sets of variables, and one of the variables in one set is equal to another variable in another set. I'm sure we'll go over an hour. I just want to make sure we get through everything. If anybody needs to go, they can go.
I'm just thinking about Trump.
Trump?
Yeah.
Oh, the debate.
But I don't care.
Yeah, I want to be anywhere but watching a TV right now. That is not a morale booster for me. Okay, t equals 0, t equals 5, t equals 10. And actually, how many more do we have? We only have, there's 2 more after this. Okay, so the question is as follows. A ball rolls down a hill. We don't know how far it goes. So it starts from rest. And if they don't say it starts from rest, imply that it starts from rest. But they'll probably tell you it starts from rest, which just means initial velocity is 0. Oh, still good. Initial velocity is 0, and they then tell you that from the 5th second to the 10th second, it's 160 meters. That's how far it goes, specifically here. And they can ask a bunch of things, like always, but let's just assume they say, what's the acceleration of the ball? They can ask for the acceleration. Let's just assume the acceleration, then we'll find out more stuff after that. Okay, well, maybe this is a really easy problem. Let's see. We don't really have x, y directions here. We just kind of have one direction. So there's no need to really break, because technically this is x and y, but because it's moving uniformly, you can just think about this maybe as the z direction. That helps. And that's kind of allowed in a case like this where it's clearly not broken up into constituents. So in this case, the v initial is equal to 0. The v final is right here. We don't know what that is. The acceleration, we don't know what that is. The time, we do know, is 5. And the displacement, delta x or delta z, we don't know what that is either. So we cannot solve for anything because remember, all of our formulas have 4 variables. If we have 3 variables, we can plug one in, but we only have 2 variables. Okay, so that's only for so this is where we would need to be really specific with our variable sets. This is the first half. First half in terms of time. Okay, well now let's look at the second half because we have more variables. Second half. Okay, v initial, well, from here to here, the v initial is here. We don't know the v initial, so that's an unknown. The v final at t equals 10, we don't know. So we don't know, so it keeps falling. It's not actually like hitting something here. So we can't assume, this is not the ground. That's an important stipulation. It's not hitting the ground. So we don't know the v final here, unknown. The delta x or delta z, here we do know, they said it goes 160 meters in the last 5 seconds. 160. The time is 5 seconds. And the acceleration, I don't know. So we could easily say, okay, we're never gonna figure this out. There's 2 variables and 2 variables. You need 3, that's unsolvable. But that's where you gotta is take a step back, take a breath, and just kind of like think about it. Because in almost all of these more difficult exam-esque problems, something from the first half is the same as something from the first half. Often it's gonna be 2 things. Well, when we think about it, the acceleration in the first half has to be the same as the acceleration in the second half. So that's one thing we know is the same. The next thing that we know is the same is the velocity final. Yeah, the velocity final for the first half is the velocity initial for the second half. And that is a common-ish thing for hard problems to do. So, okay, so I'm gonna say this is velocity mid, maybe. So this is velocity final, no more. It is now velocity mid. And this is velocity initial, no more. It is now velocity mid. Okay, so in other words, we want to find a way to express the variables in the first half and a way to express the variables in the second half and then bring them together, hopefully, thereby eliminating a variable. So, how to explain things? I want to explain things using both of these variables. So let's start with, I guess there's a couple ways you could do it. Let's see. I think I want to include, I want a formula, if I'm trying to think about how to bring them together. I want to use the formula that uses the initial, V mid, in other words, V final, and time. The one that best utilizes all of those is going to be the third formula. I probably could have used another one, but this seems to be the easiest without bringing in extra stuff, right? Like I wouldn't want to use the first or the second because then I'm bringing in another variable. And again, I probably could have, it just would make the math harder. So in other words, what I'm saying is for this bit right here, this first half, I'm just going to say, okay, V mid, which is V final for the first half, is equal to 0 plus acceleration, I don't know, times time, so plus 5a. That's how I'm expressing this. Okay. And I chose that because I don't want to use the first two formulas because they're bringing in another variable, which is not the same between the two. It just might make it trickier. Okay, so for the second half, I want to use a formula that requires, because remember, we realized already that V mid is like the thing that's linking them. So I want a formula that uses V mid, which is our initial, our delta x, and our t. That's the first one, because all the other two formulas require the V final, and I don't really want to bring in a variable that I don't have to. So for the second half, I'm just going to say, okay, delta x, which is 160, is equal to the initial, or in our case, V mid, times time, which is 5 seconds, plus 1/2 of the acceleration, which I don't know, times the time squared. Well, the time is just 5, so 5 squared. Right, and I can't solve either of these on the own. This is the whole idea. V mid and A, two variables. Here, V mid and A, two variables. But you have two equations, each with the same two variables. You can plug them in. So really what I'm saying is V mid is equal to 5A. That's great and dandy, because I can now say V mid here is 5A. So I'm going to rewrite this second equation. I'm going to combine this and this over here. So 160 is equal to V mid. Well, we realize over there from the first half that V mid is really just 5A. 5A times 5 plus 1/2 times 25 is 12.5. 12.5A. So this is 160 equals 25 plus 12.5 is 37.5 times the acceleration. 160 divided by 37.5 gives me 4.267. I know my acceleration is not 0. Couldn't be 0. That would make no sense. Otherwise, it's not rolling down the hill. I also know that it's not going to be 9.8. What is accelerating this thing down the hill? If a ball rolls down a hill, it's because of gravity, right? The biggest gravity can be is 9.8. So our answer has to be between 0 and 9.8. Now, that's not hugely helpful, but it probably eliminates one variable that says the acceleration, one of the answer choices that says the acceleration is 11.2. How could gravity accelerate something at 11.2, especially if it's at an angle? So we'd expect it to be in between 9 and 0, or 9.8 and 0. So our answer makes decent sense. And let's say we had no idea, we could have guessed that, it's between 0 and 9.8, eliminating one of the variables. Multiple choice is like really key. If you can eliminate 2, if you get 15 right, and then there's 5 where you get between 2, you've basically gotten yourself a 87.5% on average, right? Because you're going to get 2.5 of those right. That's not exactly how it works, but it's good. It's a good grade. If you can know 15 for sure and then whittle it down to 2 for 5, that's great. Okay, so this is a big takeaway. This is an important note, more important than a lot of the problems we've done so far, because this is like exam caliber. And again, it's just really key that you're like one set of variables and another set of variables. And the sets of variables can be different. It can be dropping, and there's another problem that I wanted to do, but there's no time. Some guy drops a brick, and then 2 seconds later, another guy throws a baseball down, and then you have to figure out where does the baseball catch the brick, how far below the building. And the idea there is that the time for the brick is equal to the time of the brick. So the time of the brick is just the time of the brick, whatever it is. But the time of the baseball is the time of the brick minus 2. In other words, if I have a building and I drop a brick and it falls for 2 seconds, and then I throw a baseball down. 3 seconds after I throw the baseball passes the brick. That means the time for the brick total was 5 seconds, and the time for the baseball was 3 seconds. So it's up to you to realize that those variables can be swapped. You alternatively could have said that the time of the brick is the time of the baseball plus 2, but that's another, this is an exam problem, and the one with the brick and the baseball is another straight from Adler exam problem. So that's just where there's like a million different things they could do, but realizing, this is equal to this, and then figuring out how to plug them in is very important. Historically, again, Adler's a maniac in the best way, but yeah, so okay, anyways, that's this problem. And questions on this?
How do you find,
The displacement, we didn't do that. You know what, we did the hard part. Once you solve for one variable, the problems get really easy. What's our acceleration? It's 4.267. Okay, it is 4.267. I have 1, 2, 3 variables. Tell me which formula I should use to solve for the delta x. First one, okay, I want this. I have the initial, I have the time. Okay, great, I can use that. And you could say then that that is equal to 0 times 5 plus 1/2 the acceleration, 4.267 times time squared, times 25. And 0.5 times 25 times that is 53.3. Another thing, you could have eliminated one of the variable choices. So this number, the amount of the distance it goes here, this is not drawn to scale. The distance it goes here actually turns out to be, weirdly, 1/3 the distance that it goes here. So if this went 10, this just went 30, which would make sense because I'm also going way faster here, so it should cover more ground. So you can eliminate the answer choice that says, oh, easy, the displacement from t equals 0 to t equals 5 is 160. I guarantee you that would be one of the answer choices, and it would clearly be wrong. You can't travel 160 meters here and 160 meters if it's accelerating the whole time. This distance has got to be greater than this distance. So again, that's a type of like quick, just probability thing that you can get a better chance of getting the right answer. Okay, and we have a swing rope problem, and then a traffic light problem, and then we're done. If you gotta go, totally cool. I can send you the video too. Let me make sure it's still running because I got not a lot of battery left. No, not battery. I don't have a lot of memory left. Okay, so we are doing spinning thingy. So centripetal motion is anything that's moving in a circle and has a constant velocity. So I didn't include that for some of you who I talked about centripetal motion with, but it has to have a constant velocity. If the velocity is not constant, you cannot say that the centripetal acceleration is v squared over r. It's got to be constant velocity and moving in a circle, which generally it will be, because otherwise there's not much you can do in terms of solving the problem. So they tell you that the diameter, let's say they tell you the diameter of your swing. No, let's make it even harder. They tell you the circumference of like your yo-yo swing is, I don't know, 3 meters. 3 meters equals circumference. Okay, we don't care about the circumference, we want the radius. So this is really just a fancy way of saying 3 is equal to 2 pi times the radius. I mean, that would honestly, before we even get more details, that's just like, should be another immediate. We want the radius in most of these problems. 0.477. Okay. So that's our radius. Let's say that they tell us the centripetal acceleration is 10. They say AC is equal to 10. Okay, well, 10 is equal to v squared over r. So this is equal to v squared over 0.477. And again, that's just an obnoxious way of giving you the velocity. 10 times 0.477, square root of all that. The velocity then, from there, is 2.18. Okay? So, Sam, you asked what's the difference between radial, centripetal?
Well, centripetal and radial is like the same.
Yes! Okay, I was gonna say.
But the
Tangential.
Yeah.
Yeah, sure. So, radial acceleration and centripetal acceleration are always oriented towards the center. AC, generally called centripetal. Some people call it radial. That's what the v squared over r value represents. Now, the velocity is always tangential, v tan. So it's v tan there, and it's v tan there, it's v tan there. That's what a tangent line would look like. So, I don't want to say always, but I think always. Tangential acceleration, you can't have if you have the centripetal acceleration. Because one of the conditions, we got two conditions for centripetal movement. Going in a circle, constant velocity. A tangential acceleration means that we're going around, and we're going around faster, we're going around faster, faster, faster. That means our velocity tangential is changing. If you got a changing or accelerating velocity tangential, you can't have centripetal motion, so you don't have a centripetal acceleration. So it's sort of an either or. In most of these cases, because it's chapter 3, they will, because there's a whole 2 chapters, chapters 9 and 10, where you'll deal a ton with tangential acceleration, but it will be rare. The most they'll do is, let's say that you have like a, it's hard for me to do the phone, so I'm gonna do it here. Let's say you have like a bird flying like this, but then the bird starts to also come towards us. So it's coming in a circle and it's moving like this. So it still has centripetal acceleration, but it also has a velocity going in this direction. It could even be accelerating in that direction, because that direction has nothing to do with the centripetal direction coming here, okay, corkscrew. That would be a pretty hard question. I have seen one before. It's not important enough that I want to give time to it, but I'm just saying that if, let's say if the velocity was going that way, in addition to a constant tangential velocity, you would still have centripetal motion all the same. You would just think about, okay, well now we've got velocity going in 2 directions. What are they asking about it? So in this case, we're just got a yo-yo going around. The velocity tangential, it's going to the left. They're at the max height. We found the velocity, what was it, 2.18? Yeah, so V was 2.18. Boom, we cut the rope. This is being held by some kid. This is his like Harambe hand or something. And the kid is like, it's a really tall kid. He's 2 meters tall. And the yo-yo string, how long did we say the yo-yo string was? 0.477 is R. So basically, he's spinning it around, he's spinning it around, he's spinning it around, and at the very, 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 very top, so right here, we cut it, which means the tangential velocity is just going to throw it like that way now. Those are $7, I don't care. And we just want to know how far away does it go? What's the range from where we're standing to here? Because it's going to kind of go like this. Boom, like that. This is another exam question. Well, first I want to know how high is he. So he's 2 meters tall. Like, they'll be more specific in the problem, but to where his hand is super tall. It's 2 meters, maybe he's throwing it like that. So it's 2 meters to where his hand is, but then you've got to go another 0.477 up. So it's 2.477. So honestly, we don't need anything about this problem anymore. All we wanted was to get the radius so that we could get the velocity tangential. And what this problem essentially becomes is you have a yo-yo, whatever I was spinning, that suddenly has a velocity of 2.18 to the left, where the delta y is equal to the 2 meters that the boy is plus the 0.477, so 2.477 meters. And boom, we got another projectile motion problem. I've got my x's and I've got my y's. My v is 2.18. My delta x, I don't know. My time, I don't know. And it's x velocity, so the acceleration is 0, so it's a constant velocity here. Remember, you can't really solve for much in the x direction because the velocity is constant. If I tried to plug it in, delta x equals vit plus 1/2 at squared, I would get delta x is equal to our initial velocity, 2.18, times the time plus 0. So I don't have delta x, I don't have time. So I need to get the time to solve for the displacement, essentially. Okay, and again, that's where rule of thumb, you're always going to use the y variables to solve for anything. So the velocity here, what's the vy initial? Well, it was just moving directly to the left. So if they didn't tell us there's a y velocity, we're going to assume it's 0. 0, the delta y, here we can make a choice. And we can say up is positive, we can say down is positive. I would say down is positive because we don't even have an up direction. We might as well just say that is positive. 2.477. And again, you can always say whatever you want is positive as long as you're consistent. If you say up is positive, you got to stick to it. If you say down is positive, you got to stick to it. So if down is positive, that means up is negative. So dy, delta y, it's on planet Earth, so the acceleration is negative 9.8. And I don't know the time, and I don't know the final. But we just said, you know, and this is more foresight than we usually have. Usually I say just solve blindly for stuff. But yeah.
Would the 9.8 be positive since we said down is?
Bam! Yes, that's exactly right. My own thing against me. So yeah, that's exactly right. Down is positive, so acceleration is positive. So usually we run pretty blindly, but in this case we just happen to like think about it, and we kind of have the foresight to say, okay, we need the time. And even if we didn't, we would still get the problem right just as quickly, probably, if we were just solving for anything. So I have these 3 variables. I want to plug them in to get time. I'll think about the first one. I have the delta y, I have the initial, I don't have the time, I have the acceleration, so I get the time. So I could say that this is 2.477 is equal to 0, there's no initial, plus 1/2 times 9.8 times t squared. So 2.477 divided by 4.9, square root of that, 0.711. 0.711 is equal to the time. Good, great, grand. It's from Billy Madison. None of the little kids ever get it when I say that. 0.711 equals t. Cool, so that's our time, which we're gonna plug in over here, because that's the only thing that we ever have in common, the x and the y component, 0.711. And now we can plug that in here. I know that delta x is equal to 2.18 times however long it was in the air, 0.711, times 2.18. And that means that it goes like this, and the horizontal range, the amount of time that it traveled at 2.18 meters per second was 0.711 seconds, and when I multiply those, I get 1.55 meters. Boy is spinning the yo-yo. Suddenly at the top, you cut it. It travels with that tangential velocity, I guess technically in this direction, and it lands 1.55 meters from the kid. Let me make sure this thing's still running. Yes, okay, cool. Then we've got one more, and then we're out of here. Okay, so this is another exam problem. So this was on his exam, and then he put it on his practice exam from last year. well, I guess it was the exam 2 years ago and the practice exam from last week. So you got two posts. They are 40 meters apart. So this is a street. This is a street in between these two posts. And on these things is a traffic light. So this is another really important problem, I would say. So the traffic light has a mass of 100 kilograms. And they're telling us that the where the wires attached to the traffic light is a vertical distance of like 2 meters below. And it's an equal on both sides. So it's 2 meters here. Yeah, and so, okay, so the traffic light is directly in between the posts. It's attached 2 meters above in a vertical position. So from, this is 2 meters. We thought about like from here, just that, this position. They want to know the tension in the wire. That's all they want to know at the end of the day. So the traffic light, ideally, the way traffic lights work is they just sit there and they turn green or red or yellow. They don't accelerate to the left, they don't accelerate to the right, nor up nor down. So we have a vertical equilibrium and a horizontal equilibrium, which is a fancy pants way of saying in the x direction, the sum of the forces is equal to 0, and in the y direction, the sum of the forces is equal to 0. So whatever forces on my free body diagram I have on this traffic light, they need to add up in the y and the x direction equal to 0. Because if they don't, it's accelerating in one of those directions, and it shouldn't be. So here's a new note. The tension is acting in the same direction as the displacement of this like wire. So another way of saying that is let's figure out what the triangle would be like for this. What is the x distance here? From here to here, assuming that this thing's like pretty skinny, right? If it's 40 meters and it's directly in the middle, this should be 20 meters. And this should be 20 meters. Calculator, let's make sure this is running. Yep. Okay.
We're assuming the stoplight's like.
Yeah, we're assuming it's like infinitesimally small. Yeah, that's one of those like unrealistic physics calculations we're making. If they wanted to be really specific, they could have said it's like 41 meters, and this is like 0.5 meters on both sides, but they won't. So if I want these angles, I can say 20 squared plus 2 squared, square root of that is 20.1. So this is 20.1, and that's 20.1, and I'm just getting tons of angles because it doesn't hurt to have more. And if I want to find this, I can say inverse, so I can say tan theta is 2 over 20. So inverse tan 2 over 20 gives me, we expect this is a very small angle, it looks small, and it is. Theta is equal to 5.71 degrees, and it would be the exact same on the left side as well. So the idea is the force, the tension of the rope is acting in the same direction as the displacement and direction of the rope. So in a lot of these problems, the same angles that apply for the displacement also applies for the forces. So if I have this triangle, which is 2 and 20 and 5.71 degrees, the same triangle needs to apply to my tension, and 5.71 degrees. So this is the displacement triangle, and I'm just saying it has to have the same constituent relationships as the force triangle. Force triangle being, we're breaking up this tension, remember, is just force tension. And it's at an angle, so we want to break it up into the x component and the y component. So again, the same angles that apply to the displacements apply to the forces. And that's a common thing. The way that you would know that's the case is specifically because the tension pulls in the exact same direction as this displacement of 20.1. So now, okay, shoot, we still don't have enough to figure out anything. Well, remember, this is stoplight. It's not moving left, right, up, or down. The mass is 100. So if I want to draw a good free body diagram for this, let's redraw this. I'm going to draw the traffic light just right here. Technically, it's pulling Tx to the left, Tx to the right, Ty, Ty, and the force of gravity. So it's got a lot of stuff going on. 980 newtons. So we hate angles, so we took that tension going at a weird angle and we just said Tx, Ty, as opposed to tension, force gravity. So this one sucks. We don't want that one. We would prefer to break the T into Tx, Ty. The sum of the forces in the y direction is equal to 0. It's exactly in between, so we can conclude that Ty and Ty are the same number, right? They should be. It's directly in the middle. How can one be different than the other? So if we think about it, let's just pick a direction. Let's just pick down for whatever reason. Say the sum of the forces is equal to NA. Well, 980 minus Ty minus that exact same Ty is equal to the mass, 100, times 0. The acceleration in the y direction is 0 because it's in vertical equilibrium, which just means that each of these Ty's is 490 when you do the math. 980 minus 2Ty equals 0, therefore Ty equals 490. Awesome, basically done. Ty is 490, I have an angle, I can solve for all the other stuff. Specifically, they want T, like the hypotenuse T, so I could say sine of 5.71 is equal to 490 over the hypotenuse T, and it becomes 490 divided by sine 5.71, and it's a big number. T is equal to 4925.